Now we'll move on to talk about acquisition and analysis of vibration signals. We can do the processing of vibration signals both in the time domain and in the frequency domain, and there are various analysis techniques that we can use. Here is an example of a time domain based analysis technique which is used to calculate the head injury criteria, which for example would be relevant in the determination of vehicle crash test barriers where impacts to human heads are involved, or for example in the characterization of helmets for protection of head injuries. You can see that the primary measurement is that of acceleration, but the calculation that's performed involves its integration between the start and the end of the event, a division by the time of the event. It's raised to the power 2.5 and then multiplied by the difference in start and impact and end of the time event. So we get a head injury criterion value that's presented in this plot here that is in the red curve, the purple curve. Frequency analysis or frequency domain processing is useful when we have a stationary signal, i.e. a vibration that is occurring in steady state. So we can calculate a frequency spectrum that is collected over a series of samples where the vibration is relatively constant during the time that we acquire our data of. That's unlike was the case with the previous time domain processing technique, where we're typically dealing with transient events such as impacts. In this slide you can see the difference between the time and the frequency domain for various different signal types. For a sine wave, where we have a periodic oscillation between the amplitude plus and minus with a frequency that leads to a period that in time which is 1 over the frequency domain equivalent of that signal, which is determined by implementing a fast Fourier transform typically in digital signal processing, is simply a single peak at the frequency with an amplitude that is equivalent to the amplitude of the peak of the sine wave. Alternatively, a square wave is essentially a summation of integer or odd integer harmonics of sine waves. So we have a sine wave with a frequency of f added to another sine wave with a frequency of 3f and 5f and 7f and so on. And if we do that enough times, we will have a square wave as a result. And you can see that immediately in the frequency spectrum, where we have a peak at 100 Hz, the fundamental frequency, a smaller peak at 300 Hz, 500, 700, 900, and so on as we increase up the frequency spectrum. If we look at a decaying sinusoidal frequency, then we no longer have our very sharp peak at a fixed frequency. We actually have a wider peak, and the amount of damping that we have in our decayed exponential sine wave that you can see on the left hand side, this is representative of typical vibration signal where we always have some damping. The more damping we have in the system, the quicker the decay of the sinusoid and the wider the peak that we have in the frequency domain. An impulse signal is, for example, an ideal impulse signal, which is raised from 0 to or -1 to a positive value and then drops back down some period of time afterwards. The frequency domain representation of this ideal impulse signal is simply a flat line across the entire frequency range within the frequency spectrum. Frequency analysis was essentially pioneered by Jean-Baptiste Fourier, who identified that for any given time domain signal that is continuous, it can be represented in the frequency domain as an infinite summation of sinusoidal signals, essentially with individual amplitudes and individual initial phases. So the second of the two equations here, xt cos omega t dt minus the imaginary part, or xt sine omega t dt, essentially gives us that particular frequency domain representation. So a series of points. In this case, it's a continuous function again, so it's got an infinite number of points. We can represent time domain signals in this way, and we can switch between frequency domain and time domain to our heart's content. No information is lost when we calculate the frequency or the Fourier transform to get frequency representation of a signal, so we can go back to the time domain based version of the same signal. In digital signal processing, we don't have continuous signals. We have effectively signals that are sampled with n samples within a given time period between 0 and t. The sample rate is a function of the nature of the acquisition system. We can have relatively low sample rates or increasingly high sample rates. And the nature of the frequency spectrum is a direct result of the nature of the time sampled signals. So the frequency that we have available to us in the frequency domain is related to the sample frequency, and the resolution, i.e. the time between or the distance in frequency between our individual points within the frequency spectrum, is the inverse of the time over which we capture the signal of interest. So for a 2-second time capture, we would have half Hertz frequency resolution. The fast Fourier transform is a version of the discrete Fourier transform that has been optimized to be able to be calculated rapidly in computer systems. These are no longer so relevant because the increased performance of computers has become significantly great in recent years. However, if we have an n power 2 number of data points within our signal that we want to then convert the frequency into the frequency domain, we would implement the fast Fourier transform to do that, and it gives us a very fast way of producing a frequency spectrum representation of a time domain signal. At this point in the class lecture, there will be a demonstration. So in this lecture, we've looked at the vibration of the measurement of vibration, and we've talked about why vibration is an important parameter to measure, important thing to measure, and what the optimum parameter to measure should be. We've looked at different types of transducers that enable us to make measurements directly of displacement, of velocity, and of acceleration, and we've described the performance of those transducers and their capabilities with respect to different levels of vibration and different frequencies of vibration. Additionally, we have looked at different ways of calibrating our vibration transducers. We've looked at their frequency response characteristics. We've described the way that we can determine the sensitivity and present the sensitivity using dB units. We've also described the use of dB units to look at gains of amplifiers and the attenuation that we get as a result of the implementation of an analog filter. We've also spent some time looking at signal analysis, both in the time domain, i.e. of the amplitude of the signal, but also in the frequency domain, and we've looked at the way that we can calculate frequency spectra using a fast Fourier transform in digital signal processing. There are some things to take note of. Here is an interesting reference book. Here is another interesting reference book. Here are some more references. And finally, here are some more interesting references. Have fun.